Let's begin. But you'll be there or here?
No, I'm gonna.
I'll stand here. So welcome Professor Peter Olver from the University of Minnesota. He'll give a talk on algebras of differential invariants. Welcome.
Thank you. So do I just stand near this?
Oh, it can hear you.
Yeah. Okay. So thank you very much for the invitation to come back to the Colchin seminar. I was in it in either 1988 or 1990. I couldn't quite figure out which one. And the records, the website only goes back to 2005. So in terms of the speakers. So it's a great place. Back then it was in Rutgers, of course.
Yes.
So this is the first time. This is actually the first time I've been in CUNY. And I can't resist telling another story, which I may have told back in 1988. So my thesis advisor was Garrett Burkhoff. And when I went and asked Garrett to be his student, the first thing he gave me to read was Ritt's differential algebra. And I took it and I looked at it for a couple of weeks, tried to read it, and then I went back to Garrett and I said, this is much too algebraic for my taste. I don't think I want to work in differential algebra. So it was at that stage he got me interested in Lie theory and symmetry groups. But it's kind of ironic to be in the Colchin differential algebra seminar after that history. So what I want to talk about is some mostly fairly recent work, although it's been going on now for 20-some years, about, and of course much earlier, because of course Lie himself was interested in differential invariants. It's either Lie or Halphen who was the first to come up with the notion of a differential invariant. And I've been particularly interested in recent years in the structure of the algebra they generate. It's a non-commutative differential algebra, and for various reasons, and I'll give you applications along the way, so this won't be just algebra, there will be some applied math. Really want to understand the structure of the algebra, so we'll explain this as we go along. I think I don't have a clicker, right?
No.
Just
do that. Okay, so G is going to be in this talk, G is always going to be in a Lie group, but I do know how to do most of this for Lie pseudogroups. Lie pseudogroups are much, much more technically complicated, and every time I've tried to talk about a Lie pseudogroup in a talk, I think it's gone over like a lead balloon. So we won't do Lie pseudogroups here. And I of G, I'm going to call it an algebra, but really we should be talking about sheaves of differential invariants because they're locally defined on jet spaces, for the p-dimensional submanifold. So we have the group acting on M, which has dimension little m, I don't have that here, and the submanifold has a fixed dimension p. If you want, the submanifold is the graph of a function, and most of the applications, that's how you write the differential invariants, but in general, we're interested in general submanifolds. And so the goal is to describe the structure of this in as much detail as possible. And so these are examples, very classical examples. Say Euclidean geometry, say even Euclidean geometry in the plane, you have curves in the plane, and you want to describe the differential invariants, we'll see those in great detail, or surfaces in 3 dimensions, or in n dimensions. Another one very important, particularly in image processing, but also in what's called affine geometry, but is really equiaffine geometry, is the group of volume-preserving affine transformations. Full affine, you would also add in scalings. And of course, one could go all the way to the projective group. So those are classical examples. There are many other examples that I won't get into here. I don't think I have, so classical invariant theory is another good example, but I don't have that explicitly written here. And then the official definition of an invariant to start with, I don't think I have to explain to this audience. It's just a function which doesn't change under the action of the group. And if the group acts transitive, of course, as in all the examples I gave you, there are no non-constant invariants. The only ones are the constants, which are trivial. So one way of getting interesting invariants, not the only way, but the way I'm going to talk about here is differential invariance. So now you look at the prolonged action on the derivatives. So if you think of the submanifold as the graph of a function, I'm just talking about the derivatives of that defining function, or more technically, it's the jets of the submanifold. And we're interested in an invariant of this prolonged action of the group on the space of derivatives, or the jet space in the geometric language.
So this has to hold for all k, right?
Yes and no. So initially we'll think of the group acting on JK, the K-jets. So it just depends on the K-jets. But any function of K-jets is automatically a function of all higher jets. You just project and compose, and you usually don't distinguish between the two. So the answer is both yes and no.
So you fix K, you're saying?
So you can fix K, but it's usually better to think of K as you're allowed to vary it as necessary.
Okay.
Or if you want to get slightly more technical, you could go to K equals infinity. You could talk about infinite jets.
All right.
So the same as Taylor series or formal Taylor series of the point. But any function of an infinite jet only depends on finitely many derivatives. There's no infinite dimensional manifolds in this talk.
Yeah, but this invariant is being kind of, well, I won't say the word pointwise, but it's derivatively pointwise.
Yeah, so it depends on the jet of the submanifold at a single point.
At a single point.
Yeah, another interesting way to talk about invariance is joint invariance, where you talk about the value at several points, like the distance between 2 points is a Euclidean invariant. That's a different talk, and I know a lot about that. And one can also talk about joint differential invariance, which is yet another talk, which I also know quite a lot about, but is not part of this talk.
And how does G act on the derivatives?
So the action is by I'm not sure if I have this on the slides. There was a little piece of chalk here.
There is a chalk right under the screen. Oh,
So if you have, say, just think of a curve in the plane, and think of a group element, say rotating the curve.
Okay.
So take the derivatives at this point, and then just figure out where this point goes to,
and then
and take the
tangent.
derivative there. That's the prolonged action. And you can write down, it's basically implicit differentiation, gives you explicit formulas. They're very complicated. That's part of the problem.
Right. Okay.
But they're easily defined.
Right.
Okay, and we'll probably see examples along the way of explicit computations. I want to, so here's the Euclidean group in R3. Let me do R3 instead of R2 because I want to also do surfaces. So we have the induced action on curves and surfaces. And so I don't give the explicit formulas at the moment, but let me tell you what the differential invariants are, because you know them from when you teach calculus. So for a curve in 3 dimension, there are 2 basic differential invariants: the curvature, which is the lowest order, and then the torsion, which is independent of the curvature. So they have orders 2 and 3 respectively. Okay, but there is also a notion of invariant differentiation. In this case, it's just the derivatives with respect to arc length, which is an invariant 1 form. And so you can take the derivatives and higher derivatives of curvature and torsion with respect to arc length, and those are also differential invariants, and you can explicitly write down local formulas for those.
So these are all for rigid transformations?
Yeah, so this is specifically for rigid. I'll give other examples as we go along. And this is a theorem that goes back, I guess, to Lie, that every Euclidean differential invariant of a space curve can be written as a function of those particular differential invariants. So they, in a sense, curvature and torsion generate the algebra of differential invariants by invariant differentiation. And that's a very special case of a very general theorem.
The subscript means?
Derivative with respect to S.
Okay.
So d by ds. Okay? So as I said, they generate the differential invariance of space curves on the Euclidean group. Another well-known example in Euclidean geometry is surfaces. So the basic differential invariants of the mean and Gauss curvature, which are the product and the average of the principal curvatures. That's what kappa 1, kappa 2 represent. So this goes back, of course, to Gauss. There is also a notion of invariant differentiation. So invariant differentiation is not quite the same as covariant differentiation. So usually when you learn differential geometry, you learn covariant derivatives. That takes a differential invariant to an invariant tensor. Invariant differentiation takes a differential invariant to another differential invariant, an invariant scalar. So they're very closely related to covariant differentiation, but they're slightly different. But they're also well known. You basically get the Frenet frame on the surface and you differentiate in those 2 directions. And so you get an infinite collection of independent differential invariants. And a classical theorem says that every Euclidean differential invariant can be written At least if the surface is non-umbilic, which means that kappa 1 is not equal to kappa 2. That's a complete list of the differential invariants. Okay. And so again, these generate it through invariant differentiation. As I said, the equiaffine group is another example. This is less familiar, but if you do curves under the equiaffine group, there's something known as the equiaffine curvature, which I could write down a formula for, but it would be not very enlightening. And even more complicated, an equiaffine torsion. In this case, the orders are 4 and 5, so the more complicated the group, the more complicated the differential invariance. And again, you have a similar result, that these completely generate the algebra of equiaffine differential invariance of curves. It's a pity this thing is in the way. For surfaces, this is even less familiar, but there is a literature in the differential invariance of surfaces. There's a well-known differential invariant of order 3 called the Pick invariant. There are 5 independent fourth-order invariants, which even the Pick invariant is quite complicated, but these are known in the literature. And there is an invariant, 2 invariant differentiations, just like in the case of Euclidean surfaces. And it is known that if you differentiate all 5 of these, the Pick and the fourth order invariants, you get all the differential invariants of the equiaffine surface. If you differentiate the Pick invariant, you can certainly pick up, I guess that's a pun, you can certainly pick up 2 of those fourth order invariants, but the question is, do you need the others to generate the algebra? How many do you need?
You don't know its minimum.
So that's one of the key questions. And I'm going to give you an answer to that case, but the general question, it seems very complicated. Okay, so now the general problems are to determine the structure of the algebra of differential invariance, generators, invariant differentiation, syzygies, I'll explain about those as we go along, commutators and so on. So again, as much detail as you possibly can, including the question of minimal generators. Okay, and we know some, but there's a lot to go. In fact, there's the minimal question. Okay, so the first is the question of generators. So this is a theorem that goes back, in the case of finite dimensional Lie groups, it goes back to Lie. In the case of infinite dimensional Lie pseudogroups, it goes back to Tressa. There's a version of the Lie theorem, a more recent one due to Ovsyannikov, and the ones that I collaborated on that I'll explain towards the end of the talk have to do with using the method of moving frames that I've been developing. So the ones in orange are constructive. The other ones are just existential. So we actually have a constructive way for finding the generators. And the way it works is, in any of those cases, in the pseudogroup case, there are some technical assumptions on the action. In the Lie group case, it's general. There is always a finite number of differential invariants that serve as generators. And there are exactly P independent invariant differential operators. So P, remember, was the dimension of the submanifold. So for curves, P is 1, so there's differentiation with respect to arc length. For surfaces, both equiaffine and we had 2 invariant differentiations. So the L, we don't know what the number is, but the P, we always know what the number is. And that means that every differential invariant can be locally expressed as a function of the generating invariants and their derivatives. Okay, so that's a general theorem.
What are the orders of these differential operators?
So that'll come out of the moving frame. So the constructive method based on moving frames will tell you.
Okay.
And I can give you bounds on the order based on the dimension of the group, but the bounds are typically much larger than they need be. Although for curves, often the bound is the right one. Yeah. So for curves in the plane, if G has dimension R, let me see, Euclidean is 3. 3 minus 2 is 1. The order of the D's, the order of the differential operators, they're always first order differential operators, but they have coefficients depending on derivatives. So right, if you do d by ds, so ds is the square root of 1, if the curve is given by u equals f of x, 1 plus ux squared, so d by ds is 1 over the square root plus ux squared d by dx.
Right.
So that's a typical thing. So you have first order derivative, but times some function of the jet variables. And so this part is always order 1, but this part can be, the order of this part depends on the dimension of the group. For the equiaffine group, it's something like 1 over the cube root of uxx. That's the equiaffine arc length. So
What do you mean by the order of the coefficient?
the order of the highest derivative it depends on.
Okay, all right.
Yeah.
Okay.
Okay.
So when you talk about order, you're talking back to the basic coordinate instead of, let's say, the arc length. And
That's right. Back to the basic
Back to the
coordinate
basic
in terms of the original
Original
parametrization of the curve.
Right.
I could write down similar formulas for general parametrized curves. They don't have to be graphs.
Right.
And
Right.
one then has to worry about reparametrization
Right,
and
right,
variance,
of course.
but the theory goes through just as easily.
Thanks.
Okay, so that's the very basic theorem. It's like a Hilbert basis theorem for differential invariance. The difference is that this is not an algebraic statement, it's more a statement in the language of differential geometry, of smooth functions. Means that any differential invariant is a function of the invariant, the differential invariance. The last reference, Kruglikov and Lechagan, for algebraic actions, they have versions of this theorem that give you an algebraic form of this in terms of rational differential invariance, or actually rational algebraic differential invariance. So if you look at the classical formulas, they all involve rational algebraic functions, cube roots and things like that. And their version it's not constructive, but it is in a much more algebraic language that I tend to work in. Actually, I have. So there's the Kruglikov-Lechagan version. Rational differential invariance and rational invariant differential. Rational and invariant differential operator means that the differential operators, actually, these aren't the ones that they use because these are algebraic, but you can actually write them as purely rational. And this relies on a theorem due to Rosenlicht, but is not constructive. There's a well-known theorem of Rosenlicht about the bases of rational invariance. One of the sort of general philosophies I've figured out is most algebraists like to work with polynomials, polynomial ideals, polynomial rings, polynomial invariants, but those are extremely complicated. If you do classical invariant theory, you can only get up to degree 9, but if you're willing to allow rational functions, rational invariants, you can go much, much farther. In fact, there's an explicit, for any degree binary form, there's an explicit rational generators of the rational covariance of the binary form for any degree, whereas the polynomial ones we know only know up to degree 9 or 12, depending on which tables you. So things are much easier in rational languages, I guess the message. Okay, so minimal generators. If there are more than one invariant differentiations, they may not commute. In fact, in both of the examples I showed you, they don't commute. And so there are certain commutation formulae, and the coefficients are themselves differential invariants. So this leads you into the realm of non-commutative, maybe rational differential algebra, and people like Evelyne Hubert have been very active in developing the computational tools for this. And the other thing is that in general, except for curves, for surfaces in higher dimensional submanifolds, there are relations among these differentiated invariants that hold for all submanifolds. These are what I call the syzygies. And the simplest one, the one that's most well known among differential geometers, are the Kadazzi relations among the derivatives of the principal curvatures, the derivatives of the Gaussian mean curvature. So these are sort of what I would call universal syzygies. They hold for all submanifolds. So that's what we're interested in understanding. Now, for curves, basically we understand everything. We pretty much understand the structure and the generators. There are no syzygies. There are no commutation relations. And if G is what I'll call an ordinary Lie group, so ordinary means that it has to be transitive, and then there's a technical condition called no pseudo-stabilization. But almost all group actions you can write down are ordinary, and moreover, I know what the analog of this theorem is, even if the group is not ordinary, I just don't want to write it down. Okay, so there are very few except for the intransitive actions, there are very few non-ordinary transitive actions. Anyway, so if that's true, you always have the number of generators. So G hex on an m-dimensional manifold, locally there exists m-1 generating differential invariants. So for curves in three-dimensional space, we had curvature and torsion. That's 2. M-1 is 3 minus 1 is 2. Okay? And all the other ones can be generated from them by taking derivatives with respect to the arc length element, whatever the appropriate.
So just what kind of function you allowed here?
So I work in the language of smooth functions. Yeah. But there's a sort of refined version of this in the Kruglikov-Lichagin paper where they do work, and I don't know if this theorem, actually I don't know if this theorem appears in their algebraic context. The other place to look for a more algebraic context is an old paper of Mark Green's on moving frames in the mid-70s, where he has constructive algebraic ways of getting these. Yeah. So in the purely algebraic context, I'm not quite sure if this theorem is valid. That's a good question. And I'd have to go back to Kruglikov and Lichagin to check this. I'm not sure.
And when you restrict to the algebraic context, do you expect that you would have to take more derivatives in your expressions?
Maybe not, no, because so I do know that to get the rational invariance, you don't work with, so the usual formula for curvature is uxx over 1 plus ux squared to the 3 halves. So that's of course algebraic, but not rational. So in their context, they would work with kappa squared, which is a rational function of the jet coordinates. And then in place of this, you want to get rid of the square roots. So if you take any invariant differentiation and multiply it by differential invariant, it's still invariant differentiation. So for instance, kappa d by ds is certainly a rational invariant differentiation.
But exponential functions don't appear there?
Not in their result. Yeah, so I don't know sort of a hybrid if you allowed Liouvillean functions or something like that, what is known. I don't think anything is known in that context. I mean, so the question is, of course, to get an algebraic result, you need something algebraic about the action.
Right.
So first of all, you have to define what the right notion of an algebraic group action is, which they do, and then you can try to prove an algebraic result about the invariance.
The other theorem says that m-1 is minimum number of generators.
This is minimal, yeah, there are no syzygies. So this is the one case where we know the minimal number. In the ordinary case, it's m instead of m-1, and it's slightly more technical, but it's still, it's not a difficult one. But as soon as you go to, that I already said. But as soon as you go to surfaces, things become much less clear, even if for surfaces in R3. So remember I had the pick invariant, and then I had 5 fourth order invariants, of which I could get 2 of them by differentiation. So Peter Giblin, who's a geometer in the University of Liverpool, was visiting Minnesota and asked me the question, because he was interested for basically problems in image processing, I guess, what was the minimal generating set for the equiaffine invariants? And after quite a bit of work using this moving frame technology that I'll explain at the end, by the way, you're probably going to have to cut me off at some stage, so
No,
give
there's
me...
no limit.
Oh, there's no limit. Okay, then we'll be here all night. Somebody will cut me off. I was able to prove, somewhat to his surprise, that you only needed the pick invariant. You only needed 1 differential invariant. And I sent this result off to some of the experts in affine, or what they should say, equiaffine geometry. At first they didn't believe it, and then I explained to it. There's a non-degeneracy condition, And so when they initially said this result can't be true, the counterexamples they gave to me were all degenerate in the technical sense that I have non-degenerate. So after some back and forth, they finally believed it. I'm not sure if they've made any use of it, but anyway, it is. So this is the one case where I know I have a minimal generating set, because 1 is minimal. You can't generate starting with 0 invariants. But after I figured this out, I went back and said, well, what about the Euclidean invariance? We have Gaussian mean curvature. What about trying the same argument here? And very much to my surprise, because this is of course much more well known, the algebra of Euclidean differential invariance for suitably non-degenerate surfaces is generated by only the mean curvature through invariant differentiation. So this I have not seen anywhere in the literature. It came out in about 2010, this paper of mine. So there's an explicit formula for the Gauss curvature in terms of derivatives of the invariant derivatives of the mean curvature. It's a rational fourth order formula in terms of fourth order derivatives. So there's a lot of cancellation because they're both of second order in terms of the jet variables. You differentiate the mean curvature 4 times, it'll in general be 2 plus 4 is 6, 6th order, and you take some funny combination of it, and miraculously all the 6th, 5th, 4th, and 3rd order derivatives cancel out, and you get the Gauss curvature. And if I have time, I will show you proof, or attempt to show you the proof of this one. I won't do the pick. The pick one is harder actually than this one. In fact, the formulas used in this proof were already in the literature. I just did one little extra thing, I realized. So there's this wonderful book by Guggenheimer on, it's basically a survey of Cartan's theory.
So could this cancellation thing that give you the Gauss invariant be done by computer algebra?
So it can be done using the moving frame version. So I have basically a symbolic way of treating the invariance without having to work with the explicit formulas. I think if you tried to verify this equation using the explicit formulas for Gaussian mean curvature, your Maple, Mathematica, Sage, whatever would hang up. I don't think you'll be able to get it.
They don't get it. Okay.
I haven't even tried that. It just seems it is. But as I'll show you, there's a complete symbolic calculus for treating these problems, which does not rely on the explicit formulas for any of the invariants, or even the formulas for the group itself. It only relies on the infinitesimal generators. It's quite remarkable.
So it's not a kind of elimination theory.
Well, it is, but it's a linear elimination theory. So the way I do this is by linear elimination, even though everything I'm working with is a nonlinear function.
Okay. Cool.
So we'll get to this, I hope. Okay, so in particular, we can write the Gauss curvature, some function of derivatives of the mean curve. Non-degenerate, I kind of know what that is. So certainly, so one of the objections is, what if you have a constant mean curvature of surface, say a minimal surface? If h is constant, then clearly the derivative of h is 0. So you can't get the Gauss curvature out of that. So those are degenerate. So things of, and slightly more generally, I have a class, so I know what the degenerate surfaces are, but they don't seem to appear, the more general ones than constant mean curvature, don't seem to appear in the literature, at least the literature that I'm aware of. They must have very interesting geometry, but I don't know what it is.
You mean you don't have an example of a non-degenerate surface?
Well, generically, every surface is non-degenerate.
Well, okay.
Yeah.
All right.
So all you need, so it's a little hard to check, because for that you do need the explicit formulas, but basically non-degenerate says that, well, degenerate says that if you take a derivative of the mean curvature and it's a function of the mean curvature, that's degenerate. So either 1 or 2. So as long as at least one of those is not equal,
then it's not degenerate.
Then it's not degenerate. So that's, I mean, you take a surface, as I said, generically, most surfaces you write down will be non-degenerate. Where are we now? And then we had further results. So with Eveline, we looked into conformal differential invariance. So the formulas get even worse, but we were able to prove similar results even for projective differential invariance. And then much more recently with a Turkish postdoc who was visiting me, Turkish student who was visiting me, we also did the algebra of differential invariance for ternary forms, which my student Irina Kogan had investigated, and we were able to prove a similar result. So in all cases, there's only one differential invariant needed to generate all the others. And these get increasingly more difficult to do even using the technology we have. And so you may make a conjecture by this stage, well, maybe it's always one, but I can give you an example where you need 1 million differential invariants to generate the algebra. You take this very simple group, translation in x and y, and adding a polynomial to u. And it's easy to write down the differential invariants. They're just the derivatives of order at least n plus 1. The invariant differentiations are dx and dy. And there are no syzygies. Well, the syzygies are obvious what they are. And the minimal generating set are all the differential invariants of order n plus 1. So you choose n to be 1 million, and you need 1,000,001 differential invariants needed to generate the algebra. Okay, but that's really the only example I know where you need more than one at the moment, or where I can prove you need more than one. There are a lot of examples where I don't know you only need one, and yet I can't prove that what you have is minimal, and it seems to be a very difficult question. But I think the question of what's the minimal number of generators needed for an ideal, say in the Hilbert-type theorem, I think that's an unsolvable question. There are enough hints that it might be solvable. There's more structure in it than the Hilbert question, but so far I haven't been able to get a bound on what the order of the syzygies has, a maximal bound for the order of the syzygies, and they go up and up and up in some of these. In the Euclidean case, it was already up to order 4 for the syzygy. Okay, so let me spend 10 minutes or so showing you some applications, why I'm really interested in this. So in particular, I'm going to talk about equivalence and signatures of submanifolds and applications in image processing. Of course, invariants characterize moduli spaces. Invariant differential equations, you can always, so by a general result of Lie, if under some non-degeneracy condition, any invariant differential equation could be written in terms of the differential invariance. And this leads for algorithms for finding solutions to the differential equation it's connected with the theory of symmetry reduction. Integration of ordinary differential equations, one of Lie's methods for doing that when you have symmetry is to use the differential invariance. So I kind of skipped ahead. This method of group splitting, or sometimes called group foliation of PDEs, so this goes back to Vesio, but has some recent very nice developments due to a couple of students of mine, Francis Valiquette, who's up in New Paltz, who I would recommend inviting to this seminar at some stage, and Rob Thompson, who's out in Carleton, Minnesota. They have some very nice methods for getting explicit non-invariant solutions to PDEs. And I'll briefly mention invariant variational problems. Again, this is a result of Lie, that any invariant variational problem can basically be written in terms of the differential invariance and various other things. So there's a lot of applications going on. I want to talk particularly for a little bit about the equivalence problem. So it's well known that Cartan, in some sense, solved the equivalence problem. So the basic equivalence problem is you're given two submanifolds, say two curves. When is there a group transformation that maps one to the other? So when is there a rigid motion that maps one given curve to another given curve? And Cartan solved this in terms of the differential invariance, and he said that this is true if and only if they have identical relationships or syzygies among the differential invariants. So these are a little bit different than the syzygies I mentioned before. The syzygies, the Kodazzi relations I mentioned, are the syzygies that are universal, that hold for all submanifolds. Now what you do is you take the differential invariance, you restrict to the submanifold, and you look for functional relations among the restricted differential invariants. And so Cartan said that if you have identical syzygies among all their differential invariants, then again, under modulo some technical assumptions, that's if and only if they're equivalent. And I'll give explicit examples. But the problem, of course, with any practical application of Cartan's theorem is, remember, we have infinitely many differential invariants. Not only do we have kappa S, kappa SS, and so on. So we have to check infinite number of syzygies to implement Cartan's theorem. But as Cartan already recognized, so here we go, infinite number. However, the higher order ones are always generated from a finite so that's the Lee-Tressa theorem, that you can always generate the higher order ones from that. And moreover, the higher order syzygies are always consequences of a finite number of low order syzygies. Okay, so that's true for the universal ones. That's another result of ours. But for the restricted ones, let me explain why that's true. So suppose I just have a curve in the plane. So I just have kappa and kappa S and so on. And suppose I know kappa S is a function of kappa. So that's a syzygy of order 1. Then I can just differentiate both sides with respect to arc length. And so I have kappa SS on the left-hand side, but by the chain rule I get that's equal to h prime of kappa, kappa S, but I already know kappa S in terms of kappa, so I immediately get a formula for kappa SS in terms of kappa, once I know kappa S in terms of kappa. And of course you can iterate this, so it's not too hard to believe that if you know the right number of low-order syzygies, you can generate all the higher-order ones by invariant differentiation.
You can generate some to say that it can generate all is a different matter.
That's right, yeah, but it is true, and that comes out of both the Cartan equivalence machinery, but it also comes out of the moving frame machinery, the fact that you can do this. And you can even say which ones you need once you use the moving frame machinery explicitly. Okay, so in a paper that Cherry, who's there, my wife, her last name is Shakiban, and we wrote with Alan Tannenbaum, who's nowadays in Stony Brook, who we're visiting over the weekend, and Calabi, who's just had a meeting celebrating his 95th birthday, I think. Still going strong, apparently, and a student of ours, Alan and mine, named Steve Haker. We proposed the following. Based on this. So again, back here, we only need to know kappa S and kappa to basically know everything. But of course, kappa S and kappa may be quite complicated, so getting an explicit formula for H may not be so easy, certainly in practical terms. So let's instead just regard kappa and kappa S as parametrizing a curve, and H is implicitly given by that curve. Okay, so that we proposed, and we called it, using being inspired by image processing, the signature curve. And this has been proved to be amazingly successful as a way of analyzing the equivalence problems with practical applications. So this is the result, and assuming a sufficient non-degeneracy condition, which is down, or regularity, I guess I call it here, you have the result that two curves are locally equivalent under the given group, if and only if their signature curves are identical. And there's the explicit regularity condition you need for this to be true. So this holds for the Euclidean curvature, but it equally well holds for equiaffine curvature, for projective curvature, et cetera, et cetera. Any group in the plane, you only need one differential invariant, and you can construct a signature curve. If you go to, I think this is next. Oh no, first an application. So I had a fantastic undergraduate student. He's now doing a postdoc at UCLA, but he's working in operator algebras, not in image processing anymore. But he had a project. He had an initial project, and then he finished that more or less, and he still had a few months left to go. And I wanted another project, and I'd become aware of some work on reassembling jigsaw puzzles, and I thought, well, this might be something he could at least take a look at. Maybe he can get a tiny bit to add to it. And much to my surprise, I don't know how surprised he was, it worked amazingly well. So we computed the signatures of these pieces. This is a jigsaw puzzle called the Baffler Nonagon, which you can, I think, still buy on Amazon for $19.95 or something like that. We really like it. I don't think this talk, I have a picture of the box, but the puzzle itself, there's no picture on the puzzle. Each piece is a different color, but the colors don't have anything to do with each other. And we also love it because the pieces are not standard puzzle pieces, which are more similar. These are really irregular. So we really liked it. So Dan Hoff, the student, started on this, and at first he realized that he digitized the pieces, but then he realized he wasn't doing it sufficiently accurately. So he did a very accurate digitization and some smoothing. And so he started coming back to me, well, I've got 2 pieces going together. Well, I got 5 pieces going together. And finally we tweaked the program and the algorithm. I won't go into the details. He was able to completely reassemble this in under an hour on a laptop like the Macintosh. And there's the reassembled one based from his work. And the interesting thing is we don't have to put in any a priori knowledge of what the shape of the puzzle is. In this case, it's almost a nonagon. It's called the baffler nonagon, but it's got these little extra bits on it. And the other interesting thing is that the algorithm works from the inside out. So most humans would start with the edge and work their way in. Our algorithm finds the most interesting piece, in other words, the one that has the most interesting curvature or the most interesting signature, and gradually works its way out. I don't have the movie here, but there's a wonderful movie that if you're interested.
So what is it that prevents them from making the edges actually nicer by just cutting off some of these pieces?
Cutting off some of these pieces.
I mean,
well, they could do that. Well, they're in the commercial business of selling interesting puzzles. The Baffler company has a bunch of puzzles. This is the only one that we did. Yeah, but I was quite amazed at what Dan was able to do here with his code. And we did some other puzzles. We sent it to a computer vision journal, and then they came back, well, you can do a 69-piece puzzle. What about a 6,900-piece puzzle? So Dan even went and tried a 1,000 and something piece puzzle that had less interesting edges, and we managed to get about a 100-piece chunk of it put together before the algorithm broke down. I mean, I was really worried that, because if you have a false match, pretty soon the whole thing breaks down. And I was amazed that we didn't have to confront the problem of false matches with what we did. So then the let's see, what's next? Oh, so this is work Cherry did with another wonderful undergraduate student of hers, who's currently a graduate student at Brown University, on computing signature curves of benign versus malignant breast tumors. And what they showed is that the benign ones, so the graphs here, this is kappa and this is kappa S, and the benign ones have much less variation in their signature than the malignant ones. So they got some statistically significant. Now, I wouldn't trust my diagnosis on what they did, but on the other hand, it's a proof of concept that there may be more to it than one sees. And so this is one of their graphs.
Your signature curve is just a phase diagram?
That's right. So it's like a phase plane diagram, but the axes are, instead of XY, they're kappa and kappa S. Yeah. And they've done a bunch of other cases. They also did moles and melanomas was another example of what they did, and got some very nice results on this. And what's next? Oh yeah. So what about higher dimensional things? So for space curves, you need kappa and tau, you need curvature and torsion. It turns out you only need kappa S to get a complete signature. You can generate tau S from those. That's not a very difficult argument, and after the talk, if anybody wants to see the argument, I'll show it to them. For surfaces, the standard signature in Cartan is you take H and K, Gaussian mean curvature, and their derivatives, but according to this result I showed you that you only needed H, you can actually concoct a signature with just derivatives of H, but you have to go up to second order derivatives of H to get a complete signature for generic surfaces. This has not been implemented, so I'll give you an implementation of the curve one, but we are very interested in this, or at least something close to this for Project Open. And then if you wanted to do equiaffine surfaces, I'm not sure I recommend this, but in principle one could do it.
What commas mean in indices?
These are the D, instead of D1 of H, because it didn't fit on the slide, so H comma 1 means the first invariant derivative of H.
So you need only one second order derivative, only one.
Yeah, only one.
No 1, 2, 2.
Yeah, so you can. It's not that hard to sit down once you get used to doing the calculations to figure out how you get 1, 2, 2, 1, and 2, 2 out of knowing those ones. So you need to know a little bit of the moving frame formulas to do that. It's not immediately apparent from just looking at this how you could get 1, 2, or 2, 2 out of this, but it's not so difficult. So the machinery that I've developed is in the background and gives you what you need to do. So when we finished the work on the baffler jigsaw puzzle, I sent it to a few of the people who'd worked on jigsaw puzzles in the past, and I was sent a scan of a broken ostrich egg shell by a guy who was working in Xerox PARC back in the 70s, and he said he'd never been able to do anything with it. So I got inspired. So another team, so Anna was the one who worked with Cherry, and two other of Cherry's students, and my student Rob Thompson, but this was after he was already a professor at Carleton. So we got together and we started working on 3D jigsaw puzzles of broken surfaces, broken eggshells. And so so in this case, we need kappa, kappa, S, and tau, so we have numerical ways of approximating them. And we're able to do a pretty good job on artificial jigsaw puzzles, which were generated in Mathematica by breaking up an ellipsoid, say. And we did a sort of okay job of reassembling Humpty Dumpty. So this is Marshall Byrne. He's the one who sent us the data. So this is but it's a lot of hand-holding in this.
Maybe useful in archaeology.
Well, yeah, you're ahead of me.
Oh, okay.
Actually, no, I don't have those slides. Has anyone ever heard of an elephant bird? So look up elephant bird. They were in Madagascar. They don't know when they became extinct. The latest is maybe in the 1700s, but they were like twice as tall as an ostrich, and they laid absolutely gigantic eggs, like I don't know 10 times the size of an ostrich egg, or twice the size or something. And there were lots of broken elephant bird eggs in Madagascar, and one of them sold at Christie's or one of the auction houses for something like $100,000. So there's money to be made in reassembling broken eggs. But that's not actually where we're working now. So archaeology, so you're ahead of me, that's one thing. Actually, virtual archaeology, where you just scan it. So these are pictures from Athens, from the museum there. Surgery, broken bones is another example. But what I'm working on now is a collaboration with a group in our Department of Anthropology. They're very interested in reassembling broken bones from excavation sites of humans and hominids, particularly one in Georgia, which is the earliest non-African site where they have evidence of humans. And they're very interested in who broke the bones, whether it was animals or humans, because that'll tell them something about the development of mankind. And they're using very primitive geometric tools at the moment, something called a goniometer, which I'd never heard of, but it's basically a flat square of metal with a flat pointer that rotates to measure angles. So we're in the process now of digitizing lots of broken elk bones that we know how they were broken, either by graduate students using Stone Age tools or hyenas in the Milwaukee Zoo. And then we're going to look at the geometry of the breakage using this and maybe reassemble them. So this is ongoing work. Okay, so and we have another colleague of mine, Jeff Calder. Katrina is a student in anthropology, and this is an undergraduate RU student of mine. So some of it is, here's out of standard image processing tools. This is a digitization of a typical bone. This is just a plot of mean curvature. So you can see the break edges, you can start to catch them by this. This is not up to the level of signatures yet, but we're gradually gathering steam to do this. Okay. Let's see, what do I want to do? So I already mentioned invariant different. I don't want to say much more about that. Invariant variational problems. One of the interesting problems that we solved, Irina Kogan and I solved, was the following question. So according to Lee, you can always write an invariant variational problem in terms of the differential invariance times an invariant volume form. It's also known from Lee that the Euler-Lagrangian equations inherit the symmetry and hence can be written in terms of the differential invariance. And so the question was, how do you go directly from the invariant form of the Lagrangian to the invariant form of the Euler-Lagrange equations without having to write everything out in gory detail, which may be a mess. So Irina and I solved this problem in general, and it uses the moving frames and the differential invariant algebra in great detail. And this in turn had some, well, not our work directly, but these ideas. There's some wonderful paper by Starostin and Van der Heyden on the equilibrium configurations of elastic Mobius strips, where they use these invariant formulations of them. And so it's a combination of geometry and numerics where they get these wonderful pictures, and there's sort of potential applications to carbon nanotubes and DNA and other such things. So the last part, so let me spend 10 minutes, 10 minutes, 15 minutes, something on that order. Just trying to explain to you the theory of moving frames, which is behind so that it gives you much more information about this in differential invariant algebra than we ever had before. Many of the questions I posed back when I wrote this book on equivalence, invariance, and symmetry, and I said, well, it would be really nice to know, are now in the realm of being answered, although as with some of the questions like minimal generators are still beyond what I know how to do. Okay, so very quickly, so one knows about classical moving frames in terms of frames moving along curves or surfaces. And after much study with a postdoc named Mark Fells, who was a postdoc at the time, now he's been at Utah State a long time now, this was back in the late 90s, we came up with the following definition, and this was really based on going back and reading Cartan very carefully. And I've discovered that as hard as Cartan is, you don't really understand Cartan unless you read Cartan. The reinterpretations of Cartan often miss what he was really after. And your French has to be really good, but your mathematical intuition has to be even better to do this. But anyway, so this came out of, if you read Cartan's treatment of projective curves, when he constructs the moving frame, and he goes along and he's talking about it, and he has these wonderful shortcuts and flashes of amazing insight, and then he writes down, he says, the moving frame is, and he writes down a 3x3 matrix. Not a collection, a pair of vectors moving along the curve.
Yeah.
And that was the thing that triggered. I said, wait a minute, that's not a frame, that's an element of the group.
Right.
So we came up, after sort of going back to reinterpreting other classical examples, we came up with this definition, and it turns out to be amazingly powerful. A moving frame is an equivariant map back from some open subset of the jet space in this case, although one could do this on other manifolds, back to the group. So this was the definition Mark and I came up with. Equivariant can be either left or right equivariant. So when you have G acting on the jet, the element, it either comes out to the left or it comes out with an inverse, of course, to the right. All classical moving frames are left equivariant, at least everyone I know, when you interpret them in the right way. Let's see, do I have a slide where I interpret it?
Excuse me. And the notation of rho with that script n.
So n is the order of the jet. So one could take out the n's. You could just have G acting on an arbitrary manifold and define this as the moving frame.
But what I'm asking is that, let's say rho with the bracket 1 and the rho with the bracket 2 have nothing to do with each other?
Usually well, first of all, n has to be sufficiently large for this even to exist. And secondly, one usually wants compatibility. So if you have a row bracket 3 and a row bracket 4, and you project the row bracket 4, you get the row bracket 3. So that's...
But it has nothing to do with differentiation?
No, there's no differentiation in row. No, this is just an index on row.
Right. Okay.
Sorry. So the basic theorem, and this is not a hard theorem, is when does such an equivariant map exist? It exists if and only if the group acts freely and regularly. So I'll explain what those are. So free is the only group element which fixes a single point is the identity. Okay? Or a single jet. So if you think in terms of a curve in 3D, so if you're at order 0, you're just at a point on the curve, that's not free because any rotation around that point fixes it. Now suppose you take the tangent line. What fixes the point on the curve and the tangent line? Well, you can still rotate around the tangent line. So, but if you go to the second order derivatives, the osculating circle, it's almost free. It's not quite free. There's still a sort of a rotation by 180 degrees that will fix that, but it's basically free at that stage. So that's why you've got to go up to at least order 2 to get freeness, to get the moving frame. The regularity is a global condition that the orbits are a regular foliation and doesn't come up. It's always satisfied in all the practical examples. I don't think I have the, oh, no, so you I should have put in this picture. Let's see, we don't seem to have an eraser, but that's okay, I still got enough space, I'll get the eraser. But, sorry, but in the classical case, so remember from your differential geometry, you have the unit tangent, unit normal, and the unit binormal, which is basically P plus N. So that's what's usually referred to as the moving frame of a space curve. If you read Cartan very carefully, he'll tell you that there's a fourth ingredient, which is kind of obvious, it's just the point on the curve. Maybe we'll call it P. Okay? So he calls this the moving frame of order 0. P and T together are the moving frame of order 1, because they depend on first order derivatives. And you get to order 2, but then you've got everything, so this is just... So what's the equivariant map? Well, it sends the point on the curve, or the second jet of the point on the curve, to a rotation and a translation. So this is an element of SE3. So the translation is just P. And the rotation is the 3 by 3 matrix whose columns are T, N, and B. Because they're an orthonormal frame, they form an orthogonal matrix. And I claim that's left equivariant, that map. Okay, so that's how you do convert a classical moving frame into an equivariant one. Okay, and then the construction, once you know it's free and regular, the construction is, so this is Cartan's process of normalization, or choice of a cross-section to the orbit. So choose a cross-section. So of course there's lots of cross-sections to the orbit. Cross-section just means that it intersects each orbit at one point and transversely. There's no tangent direction. So there's lots and lots of cross-sections. So here's where the art of the method comes in. The art is to choose the cross-section to make the calculations as easy as possible. Usually that means setting things to be 0, but sometimes you can't set them to be 0, so you set them equal to 1 or something like that. Okay? Now, because of freeness, if I have any point, there is a unique group element that acts, so take the point Z, look at its orbit, follow it back to the cross-section. There's a unique group element that maps the point on the cross-section to the point. That is the left moving frame. That's all there is to getting it. Okay? And of course, you could do if you want the right one, you just go the other way. The right one is the inverse of the left one. So that's basically the construction. And the thing is, it took us a year to come up with this, reading Cartan and all the other stuff with it. And then when we finally came up with it, we said, this is so simple. Somebody's got to have written this down. And you can find hints of it in the literature, but not as explicitly as that. Okay, so let me give the algebraic version of this. There's a very nice pair of papers by Eveline Hubert and Irina Kogan where they do this in a really algebraic fashion. So I tend to think as a differential geometer more than an algebraist, but if you want the sort of real algebraic version of this. So first of all, you do have to write out the explicit formulas for the prolonged group action. Those are not so easy. The cross-section, most of the time you just choose what I call a coordinate cross-section. You set R of those, R is always the dimension of the group, you set them equal to constant. So those define that cross-section. By the implicit function theorem, you're able to solve for that. And in most of the examples, you can explicitly solve it. That's the nice thing, is for all the interesting examples, you can actually explicitly solve for this. That is the moving frame map. So again, you have these algebraic equations for G. Think of them as Z is just a parameter and G is what you're trying to solve for. There are R and group parameters, R equations, so you uniquely solve for the G. And that gives you the right moving frame. Now, where are the differential invariants? So we set R of these coordinates to be constants. We got the formulas for the G, so now what we do is we substitute those formulas into all the things we didn't normalize, and that gives you the complete set of differential invariants of that order. So in a sense, you can recover these completely algebraically, and that's the beauty of the method. So let me give you a simple example. For Euclidean group acting on curves in the plane. So here's the group action. Let's see. I forget. Did I show? So this gives you, this method gives you the right moving frame. If you want the left moving frame, you have to invert the transformations in advance. And there's always a question which way. No, this is I do the right moving frame. So here's the explicit formula for Euclidean transformation in the plane. Okay, so now you do implicit differentiation as we teach in calculus. If u is a function of x, this implicitly defines v as a function of y. So we now differentiate v with respect to y. So in principle, you could give this as an exercise to your calculus class, and they will come up with these formulas, maybe. Certainly you can give it to Maple or Mathematica or something like that, and it comes up with these formulas quite nicely. So there's the prolonged action. Now, the Euclidean group has dimension 3, 2 translations, 1 rotation. So we choose 3 of these to normalize to constants, and here's where we try to make life as simple as possible. So many choices of the right-hand side will be a cross-section, but I don't want to choose this to be 73 and this to be pi over 2. It's just, the formulas will be awful. So I set them as a 0. Basically, the motto is set everything to be 0. If you can't set it to be 0, set it to be 1. And the method is self-correcting. If you make a bad choice, you won't be able to solve for all the group parameters, and you'll realize you've made a bad choice. Okay, so sometimes it's a little challenging to find a cross-section because you don't quite understand the prolonged action, but you can always... So you solve them, and out comes the formula for phi a and b, and the result is a right moving frame. Now it's actually only locally equivariant because there's an ambiguity. You can take, if you have a curve with a tangent and you rotate by 180 degrees, it doesn't change the tangent. So that's reflected in the fact that you don't have a unique specification of the branch of the inverse tangent there. But modulo that is right equivariant. Where's the, I didn't write this. If you take the left equivariant version of that, in other words, the inverse of that group transformation, you get exactly the one that I constructed there, but in the 2D case instead of the 3D case. Okay. Now, remember what I said is once you have the moving frame formulas, plug it into anything transformed, and you get an invariant. Any other function, in particular, so we normalize yv and vy. We didn't normalize vyy, v triple y, so we plug in this formula for phi into here and so on, and we exactly get the differential invariance. So we plug into vyy, we get kappa. So you can do that calculation easily. You plug into v triple y, you get d kappa by ds, which you can work out directly. But I didn't need to know anything about kappa or s. These just come out automatically. After you do this one, you say, I know what's going to come next, and it doesn't quite come next. You don't get d squared kappa by ds. You get these extra terms, and these are extremely important. These are something the moving frames will give you in general. But these are what are known as recurrence formulas, and this is a constructive proof of the theorem I already told you, the Lee-Tressa theorem for this group. By the way, where is ds? Well, or d by ds. So if you wrote dy in terms of dx, treating u as a function of x, you get this. And if I plug in the formula for phi, I get exactly ds. Similarly, the implicit differentiation operator is just the dual of this. You plug in the formula for phi, you get d by ds. So you get those as well coming right out of it. And this process of taking an object, transforming it by the group, plugging in the moving frame formula, and getting an invariant object is something I call invariantization. And it basically gives you a map that takes any ordinary object and gives you an invariant object. So differential forms go to invariant differential forms, like I just showed you, operate as variational problems. Even numerical methods, this gives you a way of constructing invariant numerical methods, and the approximations used in the jigsaw puzzles and so on were based on this idea as well. Invariantization is an algebra morphism. It does not affect the invariance. Let's see, I'm running out of time, or I've already run out of time. Oh, this is very interesting. Suppose, so we now know how to construct basically a complete system of differential invariants, but suppose somebody comes along and says, wait a minute, you don't have my differential invariant. Here, I produced it by some other crazy calculation and give it to you. And you say, but this so-called rewrite rule or replacement theorem says, no, I know how to write it. I know the basic differential invariant, so if I invariantize the jet coordinates, I get a complete system of differential invariants that are denoted by hi and I alpha k. Some of them are constant, and I call those phantom invariants. Those are basically the cross-section coordinates. The other ones are the interesting ones. Any other invariant, because invariantization does not affect invariance, so they give you this formula in terms of x's and jet coordinates, and you say, it's exactly the same formula in terms of the h's and the j's. And this is, the theorem is one of these wonderful, completely trivial theorems, but every time you apply it, it's just miraculous it works out. Okay. Now the last point, and then I'll stop, is invariantization and differentiation do not commute, unlike algebraic operations. So if I take the derivative of a function and invariantize it, that's not same as the invariant derivative of the invariantization of the function. However, we know exactly how these work, so there's more detail here that I really want to go into. But there's this what I call recurrence formula. So this is invariant differentiation of an invariant. This is invariantization of the differentiated function. And this side, these are the infinitesimal generators of the group action, which we know explicitly. In fact, they're much easier to compute than the group action itself. And these are certain wonderful invariants known as the Moore or Cartan invariants. And the interesting thing is you don't even need to know where these come from. You can compute them algebraically from these formulas. So out of these amazing formulas comes the complete structure of the algebra of differential invariants.
R is still the dimension?
Yeah, R is the dimension of the group. R is always the dimension of the group. The VNKs, the one thing you do have to know, where are we? The one thing you do have to know is the explicit formula for the prolongation of a vector field, but that's a standard formula going back to Lee in any of my books and so on. Okay, so this can all be done. And the remarkable thing is this formula, I think I have this, yeah. So, so the first thing is if you plug in one of these phantom differential invariants, this side is 0, and you get a set of algebraic equations for the R's that you can solve uniquely for the R's without having to do anything other than linear algebra. And once you know those, you get the complete set of recurrence formulas, and these, so let me skip over this. The structure of the differential invariant algebra can be determined without knowing the explicit formulas for the moving frame, the differential invariants, the invariant differential operators. It's a purely symbolic calculus. And the only ingredients are the specification of the cross-section, so just what those constants are, which coordinates you normalized in the cross-section, and the formulas for the prolonged infinitesimal generators. And so in particular, you get the following result, that if the group acts transitively, or more generally, if the infinitesimal generators depend rationally on the coordinates, then all the recurrence formulas are rational in the basic differential invariants, and so I of G is a rational non-commutative differential algebra. And it's using those, the results about Gaussian mean curvature, Pick curvature. So now the name of the game is we have all the relations by the recurrence formulas, but of course, what happens if you start iterating? How do you get the commutation formulas? We know how to do that, but basically we need a structure theory of invariant differential algebra. We have the ingredients now, but we don't have the structure theory, or what does this really tell you? What is the...
Okay, yeah. Sorry, I shouldn't be interrupting you, sorry about that.
No, okay. Absolutely.
So
you allowed me to go longer, so that it doesn't matter at all.
So how do you show that the rewriting is convergent?
There's no convergence.
Well, then how do you know that the algorithm will stop Or even,
There is no algorithm. There's
So
just
did
the
you say-
rewrite rule
yeah,
doesn't require anything. So all it requires is, here's the formula for the invariant.
you only do one step in some sense.
You just, wherever you see an X, you put an H.
Okay. So it's
Usually the H's are
so it's
constant.
just a substitution.
Wherever you see this.
It's
So
a
for instance,
substitution, right?
so let me show you a rewrite rule in action.
I mean, you don't apply the rewrite rule recursively in any
No, there's no recursion, nothing.
okay.
One step, that's the amazing thing.
So it's a whole kind of
Yeah.
homomorphism, right?
Right, so let's do this case. For the Euclidean group, we have, so X, so this is invariantization. X goes to 0, U goes to 0, UX goes to 0. That's the cross section.
Right.
Then UXX goes to kappa. Okay, so suppose somebody said, well, I know what the formula for UXX is. It's, for kappa is UXX divided by 1 plus UX squared to the 3/2.
Right.
Well, the rewrite rule says that this is equal to kappa divided by 1 plus 0 to the 3/2. And similarly,
Kappa.
yeah, similarly this, so somebody says, well, I know what kappa S is this horrible expression. How on earth are you going to produce it? Wherever you see a UX, you put a 0. Wherever you see a UXX, you put a kappa. And
So-
this cancels, this cancels, this cancels, you got kappa S.
So that's what.
And this one
Yes.
is a little more complicated. I don't have the explicit formula written out there, but maybe I had it earlier. No, I only went up to third order. I didn't write the fourth order. But if you wrote the fourth order one and then did the invariantization, you'd immediately get this formula. But this is actually a recurrence formula. This is the recurrence formula for the invariant derivative of this in terms of the invariantization of the derivative of this. And these are the correction terms. These are where the Moore-Cartan invariants start appearing. But we can explicitly write these out of any order. In fact, in this case, it's a simple algebra, and we know explicitly what all of these are. Mm-hmm. And basically, all the other results I talked about are applications of that in various disguises.
So roughly speaking, that's where the invariant theory works, because you're just saying that all these things, invariants, are determined uniquely by some what you call cross-section, is that right?
Mm-hmm.
Yeah. Is that correct?
Right. Yeah.
Okay.
Yeah.
So that's why it's invariant, because you don't care which cross-section you use,
That's right.
or any way you
Yeah.
want to compute.
So you may ask what happens if you choose a different cross-section.
Right.
Well, we know how to relate the invariant.
It just
between
makes it
two
just more complicated.
Yeah, there's an easy transfer. If you look at the paper of Olver and Kogan, where they do the algebraic version of this, they do sort of this rewrite rule just for ordinary invariants, not differential invariants. So the one thing is that the moving frame invariants are typically algebraic. So the rewrite, although the rewrite rule is very simple, there's no algorithm, there's no recursion. The generating invariants are more complicated than the ones you get by the Hilbert or other type methods. But this rewrite rule is as I said, is a completely trivial thing, but it's really powerful.
It's almost like well, I guess it's not homomorphism, but you just substitute, you're saying.
Well, it is a
In some sense,
no, it is a
because you can
homomorphism. So
In fact, what kind of homomorphism is that? Because the function that you use.
It's this. So invariantization basically defines a projection. If you just look at this line, takes functions
Right.
to invariants.
Right.
And it's a projection, meaning if you start with an invariant, you get the same invariant back again. So, or iota squared is equal to iota. So it's a projection map. But it's also an algebraic morphism.
Right.
Preserves all algebraic operations. What it does not preserve is differentiation, but we know what it does to differentiation.
You did say that the functions used need not be rational, let's say?
No, so this is all stated in the language of smooth functions.
Okay.
Yeah,
So when you say homomorphism, it's a homomorphism of smooth functions?
that's right. Yeah, but then you go to Olver and Kogan's reinterpretation, and you get it as a homomorphism of at least algebraic functions.
Okay.
And I guess with further work, maybe combining it, although nobody's done this with the Kruglikov stuff, one could actually get a rational version of this, but that's a challenge. I don't know how to do that often. So I think I'll close there. There's many more slides,
Thank you
but
very much. So in the choice of these cross sections, you say either take 0 or take 1
yeah, or something convenient.
or something convenient.
Yeah, so in some cases you have something like 1
So-
over 8 times something, and you set it equal to 1 over 8 just to get rid of the 8.
So is there any theory to guarantee that there is one choice of the?
Yeah. So it certainly in the smooth category, it's easy to see. There's always a local cross section. Global cross section is a much more difficult question, and is not always guaranteed. But in a sense, all of the Cartan theory. Remember I said at the beginning, this is really about sheaves. It's everything is local in this theory. Some people, Krugel-Kavlichargin is a more global theory, but is non-constructive. So it'd be nice to have a more constructive version of this local theory, but I have not done that. Most examples, it's almost global. There's always a singular subvariety of jet space, which I understand very well, where the action is not free and you can't extend the cross-section to. So the Euclidean curves are not a good example because they don't have a singular variety unless you went to complex curves, and then ux equals I would be an example of a singular Euclidean curve. But for the equiaffine case, the differential invariance and invariant differentiation depends on powers of uxx, and so is well known in affine differential geometry. Inflection points are not good points because you don't have classical moving frames defined there. So there's almost always a singular subvariety in the jet space where things break down, but we know a lot about the singular subvariety too, and how to deal with it.
More questions? Okay, thank you.
Thanks.
Phew.